Hello, good people. This is section 6.1 from James Stewart's Calculus Early Transcendentals book, and we are studying area between curves. So we're going to go through the Riemann sum and the development of area between curves and coming up with a general technique to calculate the area bounded by regions in the plane. All right. So first we're going to go forward with integrating vertically. This is our classic calculation of building a delta area slice. We're going to be approximating the area trapped by two curves using rectangles. And so we would typically, in our range from A to B, we would divide our interval into n delta x regions, right? And we're going to let the number of regions go to infinity. And we take an arbitrary slice in that region. We are going to calculate that delta area. It's all about building the delta area slice, and that representation or algebraic expression of that delta area slice should apply to all rectangles in the range. And we are going to be approximating the area between curves using rectangles, so we know that that's going to be a length times a width, and we know that our width is going to be delta x when we're integrating vertically because we're slicing the x-axis, and so we're dealing with delta x slices. And so what would our length be? And typically when we were doing areas under the curve, area under the curve is actually trapped by the y equal to 0 axis. But if we take a look and see if this is our f of x curve in pink and our g of x curve in blue, and looking at this height here, this is going to be our f of x height, and down here our curve in blue is going to be our g of x height. And so what is this distance? It will be top minus bottom, or the length here would be f of x minus g of x, or the top minus the bottom. So we want to create a slice that applies to all slices in the range, and so we want to scan all of the rectangles in our region and make sure that f of x is always on top and g of x is always on the bottom, so that our delta x slice representation would be f of x minus g of x. Good. And now we use our calculus with that Riemann sum. We let the number of rectangles go to infinity, and that's how we define the area between the curves, and this is our formula here. And knowing that A to B is the range of our slices. All right, so when we are given the A and the B, everything is fine, but sometimes we're not given the A and B range. So if we're only saying find the area of the region bounded by two curves, how do we find the range of our rectangles? Well, we go back to the concept of functions. And when we're given an equation, y equal to x squared, for example, what are the points that make that statement true? They make up the graph of that curve, and that curve over here in our graph is in purple, the y equal to x squared. And y equal to 8x on our curve over here to the left is going to be in green. So how do we find these points of intersection? Well, those points actually lie on both curves, so we want to set y1 equal to y2 and solve for x, or we can say if this is our f of x and this is our g of x, we want to say set f of x equal to g of x to find the points of intersection, because those will be the they will identify the range of our curves. So if we have x squared equal to 8x, that's a polynomial equation. Usually you put everything over to the other side, and set it equal to 0. We can factor or use the quadratic equation if you want, or quadratic formula. But this is easy to factor, and I can say that x is equal to 0 or x is equal to 8. So now I know that this point here is equal to 8 and this point is equal to 0 even without graphing. Now, how do we figure out without graphing which point would be on top? We can, on top of that, pun intended, we can take our points of intersection, 0 and 8, and because we found all points of intersection and because we are looking at both functions being continuous, that between 0 and 8, one function is going to be completely on top and the other one is going to be completely on the bottom. Otherwise, they would have found another point of intersection and crossed, but we found them already. So to find out which one will be on top so that we can formulate the area between the curves, we would pick a test point in between. And I always try to pick a very easy test point, and that test point here, I would pick x equal to 1, because that's something that's easy to pick. Now I'm going to check what is f of 1. F of 1 is 1 squared, and that's going to equal 1. G of 1 is going to be 8 times 1, and that's going to be equal to 8. So the bigger output is going to be the one that's on top in our function and during the entire range of 0 to 8. So we now can formulate the area be trapped between the regions. The area is going to be the integral from 0 to 8, which is the range of our slices, of the top minus the bottom function. And that's going to be 0 to 8 of 8x minus x squared. Good. And we can quickly calculate that. 8x squared divided by 2 minus x cubed over 3 from 0 to 8. We can say that that is 4x squared minus x cubed divided by 3, and we can substitute our values, right? And then minus 0, and we can simplify that to a fraction. Okay. In this next example, it says find the area of the region bounded by the curves y equal to 1 over x and y equal to square root of x, y equal to 0, and x equal to e. So I have graphed this ahead of time, and I put y equal to 1 over x in purple. I have put in green y equal to the square root of 8x. I have put in blue y equal to 0, and I have put in red x equal to e. So if I scroll in and zoom in on my graph, the area that is trapped by all of the different colors is the area of the region that we want to find. Good. So I also see if I were to draw various shells or various delta slices, these various delta slices, I still have the top function minus the bottom function are equal, but on this side, the slices are different, right? I still have delta x slices, but I'm going to want to find this point of intersection here because I'm going to want to split up my integral and say the area is equal to the sum of its parts. The whole is equal to the sum of its parts. So if I were to take this region, my different top minus bottom is going to be different than the other region. Make sense? And I can tell that this is going to be the area from square root 8x minus 0, right? That's that bottom function is 0. So what is that point? That point is the point of intersection between 1 over x and square root of 8x because that's where the green and purple collide. And so my point of intersection for those two is going to be 1 over, if I'm going to set my functions equal to each other, is going to be 1 over x equal to the square root of 8x. If I square both sides, I get 1 over x squared equal to 8x. If I move the 1 or multiply on both sides by x squared, I get 8x cubed. And if I divide by 8 on both sides, I get x cubed. And if I take the cube root of both sides, I get 1/2. Good. So I know that this point here is going to equal 1/2. And I can formulate my area is going to be the integral from 0 to 1/2 of top minus bottom plus 1/2 to e of top minus bottom. Good. And from my graph here, I can see that the top minus bottom of my first one is going to be square root 8x minus the y equal to 0, so that was minus 0, and it should look to you as the area under the curve, which is fine. And then the second one, from 1/2 to e, should be the 1 over x minus the 0 dx, and that's also the area under the curve. And in evaluating this function, we know that this is still equal to, just using radical properties, the square root of 8x is going to equal the square root of times the square root of x, and we can say that the square root of x is x to the 1/2. And here we have 1/2 to e of 1 over x dx. And so calculating these values, we end up with square root of 8x times x to the 3/2. Divided by 3/2 is times 2/3, right? And we're going to go from 0 to 1/2. The integral of 1 over x is the ln of absolute value of x, and we're going to go from 1/2 to e. And in calculating this, we end up with square root of 8, and we want to say that that is 1/2 to the 3/2. And we can actually go back and say that this is 2 over 3, right? And then we want to take away our 0, but that does equal 0. And then over here we want to say that this is going to be ln of e, take away the ln of 1/2. And we can, if you want to calculate that value of the 2 times root 8 x to the 3/2 over 3, you can rewrite this as 2 root 8 over 3, and I tend to take the square root inside, and I'm going to say that that is 1 over root 2 cubed, or you can even say that this is to the cubed power, and then we have ln of e is equal to 1, and we have 1 over, or the ln of 1/2. So we can go and simplify and take away 2 root 2, so 2 of these, leaving 1 root 2 left over, cancels with the 2, right? Or we could even go so far as to say 2 root 2 is the same as square root 8. And so I would end up with 2/3 plus 1 minus the ln of 1/2, and that's going to give me 5/3 minus the ln of 1/2. But the idea here is that sometimes you might need to, in the graphing of your region, if not all slices can be represented by the same algebraic expression, then you should split up the integral into a sum of integrals so that you have a scenario where the whole is equal to the sum of its parts. Okay. Also, sometimes when you go to find points of intersection, even without graphing, if you go to find points of intersection and you come up with more than 2, then it might be the case that the functions cross and you change which one's on top and which one's on the bottom. But then also you could have a scenario where your top function could look like this and your bottom function could look like this, in which case the blue is always underneath the red. And so you want to be careful and always pick that test point like what we did in the previous example. But in this case, in this next example, we do have where they cross. So here it says, find the area of the region bounded by the curves y equal to sine x, y equal to cosine x equal to 0, and x equal to pi over 2. So again, I chose my sine function to be in purple. I graphed my cosine function to be in blue. I graphed my x equal to 0 to be in pink. And I graphed my x equal to pi over 2 to be in green. So when I scroll in or zoom in on my graph, what is the region that is bounded by all of those colors? So I see 2 separate regions, and I see one between 0 and pi over 4, and one between pi over 4 and pi over 2. And so the total area of that region is going to be a sum of integrals. Good. And I do know that, why is that pi over 4? We know that cosine x is going to equal sine x when x is equal to pi over 4 in that range from 0 to pi over 2. We all know that cosine of pi over 4 is 1 over square root 2, and so is sine x. But that is that point that crosses both that blue and that purple, so we want to set those functions equal to each other to find that point. And now I know that my total area is going to be the area from 0 to pi over 4 of top minus bottom dx plus pi over 4 to pi over 2 of the top function minus the bottom function dx. Good. And so I can see that cosine is on top and sine is on the bottom in my region of from 0 to pi over 4. And so I'm going to get 0 to pi over 4 of cosine x minus sine x dx plus pi over 4 to pi over 2 of, and in the second region I have that the sine function is on top. And now I go forward and I evaluate the integral of cosine is sine. The integral of sine is minus cosine. And we're going to take that from 0 to pi over 4. And again, the integral of sine is minus cosine. And the integral of cosine is sine. And we still have that minus as that minus. And we're going from pi over 4 to pi over 2. Good. So this actually becomes sine x plus cosine x from 0 to pi over 4. And so we're going to get sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. And on this side, this plus is that plus. And we're going to have minus cosine, or I'll put it a little further down, plus minus cosine of pi over 2 minus sine of pi over 2. And then we want to take away our minus cosine of pi over 4 minus sine pi over 4. That's kind of ugly there. Maybe I should erase that and do that again, but I won't. And we end up with sine of pi over 4 is 1 over root 2, or maybe you want to write it as square root 2 over 2 plus square root 2 over 2, take away 0 plus 1, cosine of 0 is 1, plus, and now we have minus cosine of pi over 2 is 0, minus sine pi over 2 is minus 1, and then we have take away, and we have the negative square root 2 over 2, and we have minus square root 2 over 2. So now if I clear my parentheses and collect like terms, I end up with 2 minus 1s, which is a minus 2. And I end up with, if I distribute my minus, I get plus root 2 over 2, plus root 2 over 2, and I've got 2 of those 2 root 2s, so I have 4 root 2 over 2. And that's going to be equal to 2 root 2 minus 2. And that is the area trapped by those curves. Is that good? Hopefully that's good. All right. Sometimes it's not great to integrate vertically, and sometimes we might need to integrate horizontally. Sometimes it is pretty obvious when we are given x equal to a function of y. But it really is the case if we have a hard time calculating the top minus the bottom, because maybe the top function, like if I were to look at something that looked like this, and I could not do top minus bottom because that is the, and I went from here to here, say, to x equal to 5. I could not do a top minus bottom for that x equal to y squared because it's the same function. And so it might be difficult to do that. So what I might want to do is integrate right minus left. Okay, so that is the reason why we might want to graph our functions and make sure that every single range of our slices is the same representation and that it is easy to determine. Okay, so if we are going to integrate horizontally, how would we set that up? We're still using that concept of dividing our integral into n equal regions and forming a Riemann sum, and then letting the number of regions goes to infinity to define the area that's trapped by that curve. We recognize if we are splitting up the y-axis, we have a delta y slice, and to calculate the length of that region, we would be using a right minus left scenario. So if this is my function f of y on the right hand side, and on the left hand side I have g of y, what is that distance? That's going to be f of y minus g of y, and that's going to be a right minus a left. Good. So how would we, in this instance, find the area of the region bounded by x equal to 2y squared minus 4y, and the curve y equal to x over 2. If I solved that for x, I would get 2y equal to x. And so I have two functions here, and I'm just going to call one function x1, and I'm going to call the other function x2. So how do I find our points of intersection? That's the first thing that we want to do. So we know what the range of our slices are going to be. And so I'm going to set x1 equal to x2 and solve for y, because that's going to be our range of y delta slices. And our x1 is 2y squared. Take away 4y. Our x2 is equal to 2y. Normally we move everything over to the one side and set it equal to 0. And if I factor out a 2y, I end up with y minus 3 equal to 0. And now I have, with the zero factor property, that 2y is equal to 0 or y minus 3 is equal to 0. So I get that y is equal to 0 or y is equal to 3. So I know that I've got a range of 0 to 3 for my integral. and that I can put aside. But now which one is going to be on the right and which one is going to be on the left? If I go and take a test point, I'm going to pick a test of y equal to 1, and now I'm going to test that point, and the bigger output is the one that's going to be on the right. So if I evaluate x1 at my test point 1, I get 2 times 1 squared minus 4 times 1. That's going to be 2 minus 4, which is going to give me negative 2. And if I evaluate x of 2 evaluated at 1, my x2 function is 2 times y, so this is going to be 2 times 1, which is 2. And I see that this is the bigger output. So it is my right function. So now I can put together my area. And my area is going to be from 0 to 3 of my right minus left, dy, because it's in terms of dy. And so it's going to be from 0 to 3, and my right function is 2y, so I'm going to put 2y, and then I'm going to take away, and I'm going to make sure that I take away the entire function, so don't forget to put that in parentheses. And my entire function is 2y squared, take away 4y. So cleaning things up by distributing that, I end up with 2y minus 2y squared plus 4y, and 2y plus 4y is going to be 6y, and 6y minus 2y squared is going to be my area, and I can quickly and easily integrate that on my own. But I just wanted to show how to set that up. Okay, so I do, as a parting gesture, a parting piece of advice, it is about building the slice and making sure that the slice in the entire range of slices is the same algebraic representation. If you get more than 2 points of intersection, you're going to want to split up the integrals and do 2 separate test points and set, say, the area of one region plus the area of the other region, and make sure that you're setting up something that's either top minus bottom or right minus left. If it is difficult when you build, it's always good to graph something so that you can see, if I do top minus bottom and do a scan, is it easy to find which function is on top and which function is on bottom. If it is the same function on the top and the same function on the bottom, consider integrating horizontally and doing right minus left. Okay, and that does it for